Today I'm going to talk about the generalized Tower of Hanoi problem. Well, as you may know, the Tower of Hanoi is a famous mathematical puzzle that was introduced in the 19th century. Since then, there have been a lot of variants on the Tower of Hanoi problem. However, most of these analyses will focus on the specific problem of moving from a fixed initial configuration to a fixed final configuration. So in this investigation, I will aim to talk about the Tower of Hanoi game in a generalized sense, from a general configuration to another general configuration. So the standard Tower of Hanoi game will involve 3 pegs and n disks of different sizes. For example, here n equals to 5. And the objective of the game in the specific sense is to move all of the disks from one peg to another, subject to the rules that I can only move one peg at a time. It must be the top peg of the top disk of the peg, and I can only put it on a larger disk. So let's reformulate the problem to make it easier to parse in a mathematical sense. So I will label the disk disk 1, disk 2, disk 3, disk 4, disk 5 in increasing order of size, and I will also label the pegs peg 0, peg 1, peg 2 in clockwise order. Just imagine this is clockwise. So I will denote any configuration by an n-digit ternary code where the nth digit represents the peg that disk M is placed on. For example, so in the first example, we will see that disk 1 is on peg 1, disk 2 on peg 2, disk 3 on peg 2, and disk 4 on peg 0. So the code from right to left is 1220. And also, I will use a shortcut notation. For example, the bracketed 4 means that there are 4 ones in the notation. Okay, so the key thing to notice is that if I'm given a code, it uniquely represents the state of the puzzle, because the code represents which disks are on which peg. So it defines the specific state. So let's talk about the specific sense of moving all this from one peg to another peg in the base case, which is the standard Tower of Hanoi game. This is well known, and the number of steps required is 2 to the power n minus 1, where n is the number of disks, and the algorithm is also well known. This algorithm is unique up to reflection, and I will not prove this. So as for the general case, which is from a general configuration to another general configuration, the idea is to prove that, to show that the largest disk, when the largest disk moves, it must in fact pass through these 2 configurations. For example, if disk 4 moves from peg 0 to peg 1, it must pass through these 2 configurations. So if it is a non-repeating path, well, shortest path must be non-repeating. It cannot pass through any of these configurations more than once. So the largest moving disk cannot move between the same 2 pegs more than once. Similarly, I can do some other tricks. For example, if all of the disks are on the same peg at the beginning, then moving to any configuration will take less than 2 to the power n minus 1 moves. And a corollary is that from any configuration to any configuration, the number of moves is less than 2 to the power n minus 1. This is easily done by induction, as you can see. The 2 to the power n minus 1 is for the top n minus 1 pegs, and the 1 is for the largest peg. So if the largest m disks are on the same pegs in the initial and final configuration, they cannot move in the shortest path. And if the largest disk is on a different peg, then it moves exactly once. This can be done by contradiction, by simply counting the minimum number of steps required if these are false, and we will show that it is in fact more than the minimum we just proved. So after that, we have shown that the largest disk must move exactly once if it is on different pegs. So we can split it into 2 parts before the largest disk moves and after it moves. We can consider it as 2 halves of the general cases, and where a half general case involves all of the disks being on the same peg in the initial or final configuration. So if the largest disk does not need to move, then it does not move at all. So I reduce it to n minus 1 pegs, and if it does need to move, then it moves exactly once. It must pass through those 2 configurations. So I reduce it to a case with n minus 1 disks. So you can notice that C of n used here is in fact representing the other peg, and it serves the same purpose as A of n minus 1 because of in the new formulation it is like A of n minus 1, A of n minus 2 up to A1, where all of them are the same, obviously. So A up there in fact has the same purpose as C of n plus 1 in fact. So if I'm to propose a algorithm, it would be something like this. So we set C of n plus 1 equal to A as before, and if it is on the same peg, I don't need to add anything. If it is not, I add 2 to the power I minus 1. And I set C to be the same as the previous two. We're considering mod 3, of course. So C is set to be the same. If it does not need to move, and if it does need to move, it is set to the other peg. Just by recursion, I have the answer. It is of a time complexity n, as you can see by tabulating an example. For the general case, I will need to combine the two half general results as shown. And for a general case, I would in fact need to combine two pairs and compare the two results, since the largest disk has two ways of moving, either directly from 0 to 1 or 0 to 2 to 1. So as shown, there are counterexamples that show that I indeed need to compare this. So for other parts, I have for example, the director case where I add an additional constraint restricting some of the moves. So for each of the disks, I will color it either one of white or black, and white disks only move clockwise, black disks only move anti-clockwise. The key thing to notice is that there is only one non-repeating path from any configuration to any other configuration, as long as the largest disk needs to move. So for this case, I would define sequences Sn and Ln, where S is the shortest path for moving all of the disks from one peg to the other, to the clockwise next peg, and Li the anti-clockwise. Since there is no symmetry, you cannot have those being the same. So for just an example of working, if all of this the disks are white, I can set up recurrence relations and work out it's pretty standard. And if I have other coloring schemes, I have similar recurrence relations. For example, an alternating coloring scheme which shows a particular result, since the number of moves required is 2 to the power n minus 1, which is the same as the base case, which shows that in the base case, the odd numbered disks in fact move clockwise, and the even numbered move anti-clockwise, or vice versa. So some of the other results needed for the conclusion are that so S of n will always be less than twice of L of n, and Ln is always less than twice of Sn. So we can use this to prove a corollary that if the largest m disks are on the same peg, the shortest path does not include any moves of these m disks. For example, here we can see that if from the starting configuration on the upper left to the final configuration on the bottom left, the largest disk is on the same peg. Let's assume it is false, so the largest disk indeed moves. Then it must pass through this to the right-hand side, the pathway to the right-hand side, where the minimum number of moves required is twice the minimum of Sn and Ln, since the stack of 1, 2, 3, 4 moves, and then plus 3, since the largest disk moves 3 times. But on the I can propose an alternate pathway on the left-hand side, where the number of moves in the middle part is maximum of Sn and Ln, which is less than the right-hand side by the proposition. So in fact, it is not the shortest path. This is a contradiction. Okay, I see. After doing that, we show that the largest disk must move in a specific way, and after it reaches the destination, it cannot move again. So we can split it apart into half general cases, reducing it to the similar case as the base case as before. This is an algorithm in a similar way. For the general case, in this case, we do not need to compare results, since there is only one way of moving the largest disk. So for the final part, it is the black and white restriction case, where in this case, previously I restricted the movements of some of the disks. In this case, I restrict some configurations. So I color each disk either black or white, and same color disks cannot be stacked directly on top of each other instead of restricting the direction of movement. I have to apologize that I did not manage my time well, and I did not manage to put down all of my ideas in the paper before submitting. So I will just give a brief two-sentence overview. So some of the results are reducing it to the case where the disks alternate in color, and then showing that for the specific case, it is identical to the base case. And then I reduce the general case to sort of like the base case, so something like that. And for a conclusion, I have managed to find some algorithms for the analysis of the optimal path between general configurations in 3 different variations of the Tower of Hanoi: the standard one, the one where the disks have a restricted movement direction, and where some configurations are restricted in the black-white restriction case. The time complexity is of order n for n disks. So some of the applications would include loading cargo, where cargo are stacked on top of each other like discs and cannot swap places, and the crane picks up one from and puts it on the other. It's similar for train and aircraft switching, since they cannot switch places on the same track. Thank you. Yes.
Thank you.